Okay, so now we go from hydrogen to helium to the rest of the periodic table very, very quickly. And in fact, the rules that you need to understand to get to the rest of the periodic table are incredibly simple. And so I'm going to try to present them as simply as possible. And before we get to Hund's rules and the Aufbau principle and everything else, the first thing we have to learn how to do and get really good at is just adding stuff, but adding vectors. So the deal now is we're going to deal with multiple electrons, anywhere from 2 to 112 or whatever we're at now, and we're going to learn everything there is to learn about these things that we call term symbols. So the most important thing is we're going to deal in total quantities. The electrons lose their identity, and so we're going to have the total spin angular momentum, and that's going to be indicated with a capital S. And the degeneracy, G of S, is of course 2s plus 1, and we call that the spin degeneracy, and we tend to keep track of that. Then there's a total orbital angular momentum of those electrons buzzing around that nucleus like bees, and we're going to call that capital L, and of course there's also a degeneracy there that's also 2L plus 1. It's always 2 whatever plus 1. Please know that number, because we use it a lot. And then to top things off, we've got spin angular momentum and orbital angular momentum, and we can add them. So there can be a total angular momentum, the total angular momentum, J, and that is the sum of S and L, but it's really important to note that that's a vector sum. In fact, all of these things are always vector sums, and adding those vectors in quantum land is just a little more interesting than just adding numbers. But we'll learn the tricks to doing that quite easily. So the term symbol, very simply, looks like this. It's a superscript that's the spin degeneracy. It's a capital letter that identifies L, and then it's a bunch of values as a subscript after L that identify the total angular momentum of a bunch of different things that we call spin orbit states in most cases. And quite simply, well, G of S is the spin degeneracy, as we've already seen. So that tells you what the spin is, because we can turn that around and say the spin is the spin degeneracy minus 1 all divided by 2. So you see the spin degeneracy up there, and you call it singlet, doublet, triplet, quartet, etc. That is the way we refer to them, but it tells you the spin, okay? So if you hear quartet, then you know that you're dealing with a spin degeneracy of 4. And you can work out 4 minus 1 is 3 divided by 2 means the total spin is 3/2. Okay, that gives you a quartet. Then the L value, capital L, that's our friendly letter code, and that indicates the total L, S, P, D, F, G, etc., where we've got 0, 1, 2, 3, 4, etc. for those values. And of course there's a degeneracy there, which is 2L plus 1, as I just indicated. Now it is important that the total number of states, remember the degeneracy is the total, is an indication of the number of states associated with something. So we've got a bunch of spin states here that are various values of the total spin angular momentum, and we've got a bunch of orbital angular momentum, L states, and they're doing their thing, and the total number of states is the product of those two guys. So the total degeneracy is G of S times G of L. So you multiply the G of S value, which is just sitting there, because that's how we identify it. You figure out the degeneracy associated with that capital L, 2 times that plus 1. You multiply them together, and that tells you the total number of quantum states associated with this particular thing that we call a term. Now, those J values, those we list down as a subscript. We list every allowed value of J, and we'll learn in a second how we figure out those allowed values. And we go from the lowest energy one to the highest energy one, and they're separated by 1, which is part of the rules that we'll learn about in a second. So the first one is the lowest value plus 1, the lowest value plus 2, etc., till we get to the biggest value allowed. Now the total degeneracy down there, G of J, of any individual J, is of course twice J, whatever that is, plus 1. The total degeneracy in the J states is the sum of all of those individual G of J's. Okay? And that's because the energies are actually distinct. So we take the degeneracy of each of those J states that are allowed, and we add them all up. Now that's also a total degeneracy, and in fact they have to be the same. So that has to be equal to that total degeneracy up there that we got by multiplying g of s times g of l. Okay? So that is a check. You have to check when you write down a term symbol that when you figure out the total number of states by multiplying the spin degeneracy times the degeneracy associated with the orbital angular momentum to get the total number of states, that's the same thing as when you identify these spin orbit states, these j values down at the bottom, and add up all of the degeneracies associated with those various j values. They need to match. Okay? And you should know how to do that. We need to add vectors here. And adding vectors in the quantum world is a little more interesting than adding things, scalars or vectors, in sort of general math land. And specifically, it's because the z value of all of these angular momenta must come in chunks of 1 h bar. That's the currency of angular momentum exchange, and as a consequence, everything is kind of rigidly regulated by the central quantum bank, so that everything comes in these little ticks of 1 h bar. They can be 1, 2, 3, 4, 5. They can be integers. They can be 1/2, 3/2, 5/2, etc. The odd, the half integer value separations, but the interval between them is always going to have to be h bar. So basically, we're going to have a big vector and a little vector. And I use Klein, the German K-L-E-I, so it's Klein to indicate little because I want to avoid that letter S. So it's like it's small or little, but small is S and little is L, so I use Klein. Okay, so we've got I should call it Gross and Klein, but I don't. So we have big and Klein here, and the big vector is the larger of the two vectors, and Klein is the littler of the two vectors. And either one of those might be spin or orbital angular momentum, or it might be some sort of intermediate calculation. It doesn't matter. These are the basic rules for adding two vectors in quantum angular momentum world when one is larger than the other. So you identify the larger one, and you identify the smaller one, and then you add them together like this. The best you can ever do is to line them up. The worst you can ever do is to anti-align them. So we've got small Klein there and big, and the biggest value you can get is big plus Klein, and the littlest value you can possibly get is big minus Klein, and you're going to get every interval of 1 in between. That's it. Okay? That is all there is to it. You take the two vectors, you take the largest possible combination, you take the smallest value you can get if you subtract the little one from the larger one. And again, big and Klein can be either the total spin or the total orbital angular momentum. You get cases of either one. Sometimes you got a high spin system with low orbital angular momentum, and in other cases you have high orbital angular momentum and low spin. And in fact, the way things work out, that's the way it tends to play out. In order to get lots and lots of orbital angular momentum, you got to get low spin, and when you have in order to get very low or very high spin, you tend to have very low total orbital angular momentum. So you really do get one or the other being the larger case. But that's all there is. That is the rule. The biggest deal here, the easiest way to make mistakes, is to say that they're going to go to 0. They don't necessarily go to 0. In fact, going to 0 is kind of dumb luck, right? So big B minus K is not necessarily all the way down to 0. And that's why you need to do that check of the J values that I showed you on the previous page, because people typically make that error down there. So you go from the big value plus the Klein value to the big value minus the Klein value in steps of 1. That's it. That's how you add the vectors in quantum world. Now, the next thing is, how do we actually figure out the value of capital L if we have some subshell? And basically this works for any subshell. So if I have all of the P's, the D's, the F's, whatever I'm trying to fill up. And again, The technique is really pretty simple. It's very, very hard to try to imagine how all these things fit together with different vectors pointing in different directions. But it's really, really easy to figure out the largest z component of the deal. And that's what we do. So we actually fill up the orbitals in the way that you've already been taught to. So you've been taught to do all this. And we'll go through Hund's rules in a second. But so basically, let's look at a p. So the way when we lay out those three orbitals associated with a p atomic orbital, that's the different values of m sub l, -1, 0, and +1. And I typically write them in this order because I like small values to be to the left and large values to be to the right. And so let's look at a case where we have a configuration. We've got two electrons, and we've got them in the p orbital, a p2 configuration. And here I have put, if I have both spins up, I can't put both up spins in the -1 because they're not allowed to both be in the -1 and up. So if I have two spins up, the most extreme case I can get is to put one in the -1 and one in the 0. And so the m value associated with that, the m sub l, the total z component of the orbital angular momentum there, is just -1 plus 0, and that's equal to -1, and I take the absolute value of that, and that gives me 1. So the capital L value, the total orbital angular momentum value, is 1, and that means that my big letter is a p. So SP, that's 1, so I get a p. And of course I've got these two spins here that are aligned with each other, and so my total spin is a half plus a half is equal to 1, and that's why I have a triplet. Now the other possibility is that I could have the two spins aligned with each other. And let's use the other side to make those extreme. So I align them both. I can put an up and down in the +1. So I get +1 plus +1 equals 2. And now my total orbital angular momentum is 2. And so that's SPD. That's D. Okay? But the spin is 1/2 minus 1/2 is 0. So this is a singlet D term symbol. So I have two cases, where I have two electrons in the p orbitals, okay? One, when the spins are aligned, is going to be a triplet p, and the other, when the spins are anti-aligned, is going to be a singlet D. Now there are other possible cases, but we're not going to worry about those guys. Just don't try to push around those spins into the intermediate cases where they're not maximal. You get into a big mess because you find out an m sub z value, but you've got no idea what L value it's associated with. So just don't do it, okay? All this works for that I'm telling you how to do here really easily is to figure out the maximum allowed. Because there we know if we push it to the extreme, that is actually telling us what the total value is as well, because the maximum m sub z is equal to the L value, right? So those are the two ways we can maximize the m sub z with the spins aligned or anti-aligned, and we get the triplet p and the singlet D term symbol. The other big deal here, well worth noting, is that I've got electrons in the little p orbital, so that the angular momentum of the individual electrons is 1, the total orbital angular momentum quantum number, but the two of them, when they kind of conspire together and anti-align their spins in green there, the overall term symbol is a capital D, right? The total orbital angular momentum, if I have two electrons with 1 unit of angular momentum, can get itself as high as 2. It can get as high as 2, and so I can get a D. I have to anti-align their spins, and so it's a singlet. So the little letter associated with the orbital is not necessarily the same as the capital letter associated with the total. So do not confuse the two of them. Work out what the total is via this methodology. We can take these two term symbols, and if this is all of the electrons that we have in a not completely filled subshell, this actually will be the total term symbol. So we can add the spin and the orbital angular momentum vectors and figure out the J values. So let's start with the triplet P. So the triplet P has a spin of 1, and it's got an orbital angular momentum of 1. And so I can go anywhere from the total J equals 0 all the way up to a total J equals 2. Because 1 minus 1 is 0, and 1 plus 1 is 2. So I'm going to have 0, 1, and 2 as an allowed value. So the full term symbol here is triplet P210. Those are all of the possibilities we can get, and then we have to do our check to make sure we did it right. So triplet P, well, the triplet's a triplet. The P is L is equal to 1, and so that's also there are 3 states there, and that means there's 9 total states. So with the triplet and the P, I figure out there are 9 total states. And then from the J values of 2, 1, and 0, I take the degeneracies of each of those, and I've got 5 and 3 and 1. Twice each of those plus 1. And 5 plus 3 plus 1 is equal to 9, so it checks. I've got 9 states in either case. Now the other one is the singlet D. So with the singlet D, I have a spin of 0, but an orbital angular momentum of 2, and so my total J value's got to be 2, because the spin is 0 and it does nothing to it. So I have a singlet D2 is the full term symbol there. And 1 times 5 is 5, and 2s plus 1 is 5, so we get 5. Those are pretty easily. If I've got a singlet or an S, then there's only going to be one J value, because one of the two total vectors is equal to 0, and it's pretty easy to do that combination.